potential. And then when we transitioned to the new book, I didn't make that code switch, and so I threw a capacitor problem on the test 1A, even though it wasn't officially on that test.
Have you ever had tests where like everyone just miserably failed?
I have had tests where a good chunk of people miserably tanked.
But I didn't like the pretext, this is the first one.
No, not the pre-test, but it's usually the last test because there's more material on it. People are burned out.
You ever had like a 10 average or something?
Formal lab report, when I was doing formal lab reports, those averages were in the 30s out of 100.
That is awful.
Yes, it is.
They just not write it well, or?
You know, I even set it up for, all you have to do is a find, control F, and just look for one of these words. If it's in there, change it. Like prove, proven, proof. Those words shouldn't be in there. If you use second person, just do a search on YOUs, all the you, your, yours, change them. And people don't do that. I shouldn't say that. A vast majority of people did not do it. All right. Given our exploration of capacitors, let's play around with them a little bit more. How many of you have had this stuff before in some form of high school?
Somewhat-ish.
That's it? Okay. I got two parallel plates hooked to a power supply. Positive, negative plate. Now what I'm going to do is I'm going to take that connection and I'm going to split it. So instead of hitting the plate right there, I'm going to now have it hit there, and this one I'm going to do the same. As the capacitance change,
No, because doesn't it just spread evenly throughout the plate?
yeah. So my capacitance doesn't change at all, just because I now have two connections instead of one. Matter of fact, it's impossible to have one connection. Any wire's got some thickness to it. It might be small, but it's got some thickness, so I am touching more than one spot. I'm now going to take this and I am going to split it.
Whoa.
Assume that that cut doesn't take up any of the area appreciably. Has my total capacitance changed? Because if we think about capacitance being charged over delta V, has my voltage changed?
No.
Okay.
No.
Has the amount of charge on the plates changed?
No.
So my total capacitance hasn't changed at all. But in reality, I've got two capacitors here. They're smaller than what I started with. Each one is separate. So if I started out with some capacitor C and now I split it like that, I now have capacitor 1, capacitor 2. Let's apply Kirchhoff's rules to sort of double back on one of the things. The voltage hasn't changed. So I start here. Remember, Kirchhoff's rule is that if I end up back where I started, then my total gains and losses is 0. So I come up here, I go down this path, go across here, and then back. So if I gain, say, 20 volts, I'm going to lose 20 volts across that. Or I can go this way, this path, down, around, back to where I started. If I gain 20 volts here, I lose 20 volts there. The voltage across the plates has not changed. The fact that my potential difference between the two, so whatever, from that spot to that spot, my potential difference is the same whichever path I take. If delta V is same across two paths, I'm going to try to keep it simple language. You can pick apart the wording if you want, but hopefully you'll go with the spirit of what I'm saying here. All right, that's bugging me. Plus two paths with same start and end. The paths are parallel. These are known as parallel capacitors. Parallel capacitor, got a power supply here, cruising up. I split, capacitor here, capacitor there. That would be more the schematic of parallel capacitors. I have, with the same start and end, I have the same potential drop across both of them. The equivalent capacitance for parallel capacitors. C1 plus C2 plus however many I have. So you're doing a design for a taser and they say, all right, we need a 50 farad capacitor in there. And so you design, you pull out the 50 farad capacitor. Good thing, because they said 50 because that's the largest capacitor you had. And then they come back and say, no, we want 100. 100 farads. And you go, we don't have one. That's okay. You got two 50s, put them in parallel, you got 100.
Nice. What's that? Is that capacitor on the bottom there?
That word right there?
Yes.
Yes.
Okay.
So the equivalent capacitance of parallel capacitors is just the sum of the capacitors. Oops, not that. Let's do that more formally than just sort of the conceptual approach right there. Call this C1, C2. C1 would be Q1 over delta V. C2 is equal to Q2 over delta V. I guess right now it's sticking 1 and 2. I know that, and I want to find the equivalent capacitance, which is just going to be some charge over delta V. Well, all my delta V's are the same. So this becomes, actually start going in the wrong circle at this point. So the total charge that's being stored is Q1 plus Q2 over delta V. And again, the potential drop across either path is the same because if I start and end at the same spot, the potential difference has to be the same. So it's Q1 over delta V plus Q2 over delta V. And since delta V1 and delta V2 are the same, this just becomes C1 plus C2. Slightly more formal than the hand waving I did over there. So quick plug and chug. C1 equals 3 farads and C2 equals 4 farads. Then my equivalent capacitance is,
7 farads.
thank you. It's as simple as that. Questions before we make it look more harder? More harder? Before we make it look harder. Then let's make it look harder. Hopefully without making them seasick. So I got my battery here, kind of cruising along, got a capacitor here, got a capacitor here, and then back. These are not in parallel. If I think about current flow, I have current flowing out of the battery, and I have current flowing onto this plate right here, which is going to force a current flow between the plates, which forces a current flow this way. The current does not have any other path to take. It has to travel in that circuit. If that's the case, if my current is staying the same across each of them, then this is series. Well, I have some potential difference across my power, or created by my power supply. I'm going to have some potential difference across capacitor 1, and some potential difference across capacitor 2. So I know that delta V, the potential difference across my power supply has got to be minus delta V1 minus delta V2, going to be 0. I know for capacitor, that's equal to Q over delta V. So delta V is Q divided by the capacitance. Oh, no. So I have delta V equals delta V1 plus delta V2. This is the charge over my equivalent capacitance. Is equal to my charge over capacitor 1 plus my charge over capacitor 2. Because the current's the same, that means that whatever charge I'm putting on one plate, so if this is 3 coulombs here, this plate will be negative 3 coulombs, this plate will be positive 3 coulombs, this plate will be negative 3 coulombs, and so on. So the charge on each of the plates is the same in series. So my Q's are all the same. And so I have 1 over my equivalent capacitance is equal to 1 over C1 plus 1 over C2.
Could you explain why sorry, I missed the explanation, why the charges are all the same, why the Q's are all the same?
For the parallel plate capacitor, when you get a charge on one plate, it forces a charge off another plate. Or if I get an electron on the negative plate, it's going to force an electron off the positive plate. And so for every So if I get an electron here, it's going to chase an electron over to this plate. So this gets an electron, which will chase one off of this plate. So this will be -1, that becomes +1, that's -1 and +1. The charges on the plates, the magnitude of the charges on the plates will be the same.
Could we assume that the charges on the whole system is distributed evenly, that like a charge on any particular point should be the same?
The surface charge density on the plate is the same?
Yeah.
We assume that the surface charge density is uniform on a plate. It is possible for the surface charge density not to be the same on each plate if the plates are different sizes. If they're the same size and totally parallel, you know, under the simple situation, or the standard physics 252 situation, then the surface charge density is probably gonna be the same for every plate.
Okay, thank you.
So for series capacitors, 1 over the equivalent capacitance is basically the sum of 1 over the reciprocal of the equivalent capacitance is the sum of the reciprocal of the individual capacitances. Therefore, if C1 is 3 farads and C2 is 4 farads, what's the equivalent capacitance?
7.
If they were in parallel, yes,
Seven.
these are in series.
7 over 12 farads.
You made the most common mistake there is of this.
7 over 12, 1 over farad.
Okay, those would be the correct units there, but I want capacitance. Take it step by step.
12 over 7 farads.
There you go. 1 over the equivalent capacitance is 1 over 4 plus 1 over 3, which is 7/12. So my equivalent capacitance is 12/7 farads. Don't forget to take the reciprocal at the end. That is the most common mistake.
I can see that.
So you would lower your capacitance by sticking another one in series.
So you just flip them. The 7 over 12.
Yeah, because that's 1 over the equivalent. Yeah. All right, ready for me to make it a little harder? Got one head shaking no. All the rest of you, I'm assuming your silence is yes. And a bonus, you get the irritate chance. I don't think they were thinking it. All right, we're gonna do it anyway. We get 3 farads, 2 farads, 4 farads, 5 farads. What is the equivalent capacitance? I recommend, when faced with one of these problems, first, identify the junctions. Where can current split? Well, current can
Is that
split.
bottom one 5?
Yes, that is fine. Sorry. Questions about my handwriting before we continue?
I was just still.
Where's the battery?
Pardon?
Where's the battery?
It still has an equivalent capacitance without a battery in it, but if you want a battery, we can stick one right there.
Whoa, it's round now.
I have a junction here and a junction there. That tells me I got these 2 paths here, these are in parallel with each other. So the first thing I do is I can add stuff that's in parallel or stuff that's in series. I can't add stuff that's a mix yet. I do it step by step. So I'm gonna do the parallel first. So it gives me a 3 farad. What is this equivalent?
6.
6 farad.
And so I replace this 2 parallels with a single 6 farad. So now I have a series because any current that flows on here has to go across the others. And so 1 over my equivalent capacitance, 1/3 plus 1/6 plus 1/5. See, 30 is the common denominator, so I got, I think 21/30ths. Is 10/7. Now, some math teachers say that if you can do it in fractions, keep it in fractions because that's an accurate result. If you go to decimals, you're going to be rounding off. But this is physics. Any measurement is rounding off in it. That 3 farads, that's the one significant figure that could be anywhere from 2.5 to 3.5 farads. So we're rounding already, so I'm fine with decimals.
On an assignment, it would be okay to leave it as a fraction.
Sure. Yeah, I don't have a problem with the fraction either. I have a calculator, I can figure out what that is in decimal. All right, questions to hear before I make it look more complicated? All right, I'm gonna erase this. Now, whenever